4.2 we started last time. This was on area. And we had taken a look at some formulas, I guess, if you will, or properties of the way summations work. And these were the 4 properties that we encountered. And we talked about the fact that if we went back to the first problem that we did and we used the formulas, that it worked the same way as if we individually evaluated the 6 index points, right? And then found the same value. And of course, it being overkill to do that in that way because finding 6 values is no big deal. However, finding 16 values becomes a little bit more cumbersome. And the more values we have, the more cumbersome it becomes. So we're going to use the summation rules to compute the sum of these. All right, so what we want to keep in mind as we're taking a look at these is that all those constant multipliers, some different kinds of properties that we had back with limits and derivatives, they all extend into this idea as well. So as we're taking a look at this, the first thing that we actually need to do is we need to separate the pieces that we have. So there's going to be a location right here that gets separated, between the subtraction of the 2 pieces and the coefficient right here at the beginning. Wow, that was really thick. Let's try that again. The coefficient right here at the beginning, the 5, can be pulled out as a constant multiplier in front. So when we rewrite this, and we do need to rewrite it in order to use those sum rules, the 5 comes out in front. This is I equals 1 to 16 of I, and then minus the summation of 4, I equals 1 to 16, like this. So that's the first step. When it's in that form, we actually have 2 pieces for which we can use those properties on the previous slide. Those are the 2 pieces. So the first piece, that's the summation of just I, it says, okay, the 5 stays out in front. It says we take the number of terms, which would be 16, right, the n at the top, and we add that, or multiply that by the value with 1 more added, so 17, and divide by 2. That's what that property says. The second one here that's circled in red is the first property over here. And it says that we simply multiply that constant, in our case it was a 4, by the number of terms, so 4 times 16. And then we apply arithmetic. Add, subtract, multiply, divide, those sorts of things. So grab a calculator real quick. What was that? Did you have a value? What?
It's 256 plus 16 divided by 2.
Are you multiplying all that in your head?
That means 16 squared.
Oh, gotcha. That's a good way to do that, yeah. I don't have the individual pieces multiplied out myself personally. Did anybody get a total for this at this point? Nick's back there trying to do everything in his head. Impressive mental math. I'll give you that. That's all you got. Okay. Did anybody get a value? Kaylee's typing it in. What'd you get, right, Anthony? 616. That's what's on my paper. Fantastic. It is 616. Okay. Is that good for everybody? We broke it down into something that involved basic arithmetic, like elementary school stuff, right? This is my 5th graders. They can do that part. They can't do the part above it, but they can do the part there at the end with the multiplication and division and so forth. Yeah. Okay. Very good. Not in their head, though. On paper with pencils. Okay, let's do the same thing here. You'll notice here there's a product, right? The n is multiplied by n minus 1. We don't have over here anything that tells us what to do about products. Okay, just like when we had derivatives, there's a way to do it with a product rule, if it's complicated enough, but there were other ways to do things as well. What did we have to do when there's a product? Separate it, like distribute maybe. Would that work? Yeah, we can distribute. Let's distribute when possible so that we can actually have the ability to use those properties. And take a look here. We're actually starting at n equal to 4, so I'm going to have to show you what happens when n is not equal to 1 at the bottom. They're using n here instead of I. If that bothers you, because it does feel a little bit funny, you can change all the n's to i's. It doesn't matter. The reason it feels a little funny, I think, to me, when I look at it, is because over here, the n is the number on top, and now we're calling the n the value on bottom. So if that bothers you, just change them all to i's or k's or whatever other letter you'd like instead of n. Okay? When it gets to this point, it looks very much like the problem before, where I have addition of, or in this case, subtraction of 2 different values. So we can separate that as well. So this is the summation from n equals 4 to 140 of n squared minus the sum from n equals 4 to 140 of n. Okay? Keep ignoring the fact for the moment that n is equal to 4 at the bottom, that the index starts at 4. So what we have, if the index were to start at the number 1, okay, if the index were to start at the number 1, we would apply the properties we had before. So I'm going to write them as though they start at 1, and then I'm going to show you what happens because they don't. So we're going to change this from n equals 1 to n equals 40 of n squared minus the summation from n equals 1 to 140 of n. Now clearly that's not the same thing. I can't just change numbers and expect to get the same value. That's ridiculous, right? So there's got to be some sort of compensation. It's kind of like when you're working with equations. If I add something to one side of the equation, I have to add it to the other side. Or if I add something to one side of the equation, I can subtract it also from that side of the equation if I'm doing something like maybe completing the square. Right? There's a balance, there's a compensation for when we make changes like that. So this is the compensation. What we did is we added n, what happens when n is equal to 1, when n is equal to 2, and when n is equal to 3. Right? We added in 3 extra terms. In particular, we added in a1, a2, and a3. So I need to subtract off a1 and a2 and a3. Okay? Jot yourself a note so you can look back at this and see why you did this. This change right here, changing from n equal 4 to n equal 1, meant that I increased the number of terms in the summation. In essence, I had the index start at A1 and then to do A2 and then A3. Those are the 3 additional terms I had. So since I included them here, now I have to exclude them at the end to subtract them off. Now finding A1, A2, and A3, we've done that. We did that last time. We take this original one expression and we evaluate it at 1, at 2, and at 3. So we can even leave it in that factored form if you wish. This is saying I'm going to multiply 1 times 1 minus 1. Well, that's 0. I'm going to multiply 2 times 2 minus 1. That's 2. And I'm going to multiply 3 times 3 minus 1, and that gives me 6. So these values here at the end are, in fact, 0, 2, and 6 that I have to subtract off. Okay? Everything at the beginning stays the same, so I'll just copy that and paste it. Okay, is everybody okay so far? That's something different. We have not done that before. Now, the summations at the beginning, if I work my way back up here, since I'm running out of space, we can use those properties from before. So we have n squared. We haven't used that one actually yet. N squared, or in this case it looks like I squared, is taking the top value plus 1, double the top value plus 1, and then divide by 6. Right? It's this property right here that I'm looking at. So over here I have the n value, that's 140. And then 1 plus 1, that's 141. And then I need to double the n value. What's 2n? What's 2 times my top index? All right, I'm at 140, so it's at 280, and then I add 1. So 281, and then divide by 6. Okay, so what I did over here, maybe I should write down the equational, sort of the formula part. This was n, this is n plus 1, and this is 2n plus 1, where the value that I'm talking about as n here is this number 140. It's always the top value that we're substituting in here, so 140. Okay? And then the other piece is subtracted, and it's supposed to be n, that's the 140, n plus 1, that's 141, divided by 2. So again, this is n and n plus 1. That's what those are. And then after all of that is said and done, I'm supposed to do something else at the end. What should I be doing? Yeah, subtracting off how many? Yeah, 8, because it's 2 and 6, right? all arithmetic in your calculator, right? Just grab your calculator and compute 140 times 141 times 281 divided by 6, and then 140 times 141 divided by 2, and then subtract those two quantities at the end. What do you get? That's what I have too, 914,612. And this is actually a really good example. I mean, this one's not bad. I mean, I don't want to do this 16 times, all right? I mean, I really don't. But I absolutely am not about to do this 140 times. Or even 137, because it technically starts at 4 and goes up to 140, right? I'm not doing that. So these properties become infinitely valuable at this particular problem. Any questions on that? Okay. So one of the things that I said is that you need to give me until the end of the week for everything to connect all together. So why in the world are we talking about these summations when we were just talking about antiderivatives? Well, there's another piece going on that I need to explain before I can connect all the pieces together. All right? And that's what's happening on this next piece of information. So when you're in geometry in high school, and even in 7th, I think it shows up in 6th and 7th grade math, where you're learning how to find areas of shapes. In particular, you're able to find areas of very specific shapes, like areas of squares, areas of rectangles, areas of triangles, circles, ovals, different things like that have concrete formulas, and you can find their area. Agreed? Okay. So the very first day of class and into the second day of the class, one of the things that I told you is that in calculus, you're able to find area of these sort of arbitrary shapes. They aren't concretely these formulas that you've seen before. They have this arbitrariness to them. And that's actually what we're encountering right now. So imagine that you have this curve. And what you're wanting to do is you're wanting to find the area of the region underneath a specific location of the curve. So I'm going to draw this in so that you have an image in mind. So we're going to take the area between my two red lines, okay? The area is going from some A value on the x-axis to some B value. And what we're trying to find is the area of this very oddly shaped region, right? All of this in here. It is not a rectangle. It is not a triangle. It is not a circle. It is not any of those shapes that you've encountered before that have nice, neat, clear-cut formulas. So what do you do about that? Well, you need calculus, okay? So what we're doing in this section of material is we're talking about ways to approximate that value, okay? Do you remember when we first encountered slopes of tangent lines and we did these numerical methods where I said we're letting the values get closer and closer and closer, and so we did like 0.1 and 0.01 and 0.001, remember that? And it was an approximation for how to get the slope of the tangent line, right? That's what this is. This is the equivalent of that. This is the approximation for getting the area under this curve. And we do it using pre-calculus, okay, using things that you've done before this class. And in particular, what you see written here is that the area here could be approximated using rectangles. But there are 3 different approaches to determining the height of the rectangles. So imagine, I'm just going to draw 4 regions in between. Imagine we split this in half. Okay, pretend. It's not when you do all the way to the top and bottom, and in half again. So this is into 4 regions. They should look like they're equal, and I can't get this to work. All right, we'll just go with that. They look like they're about equal in width. That's my intent anyway. And they look almost like rectangles in the sense that they're constant width, right? But the heights of them, how do I decide what the height is? Well, there's lots of ways that you could decide the height. We're going to talk about 3 specific ways, 3 ways that are typically done. One way to decide the height is to say, you know what, I'm just going to use the left-hand side. Every single time, I'm going to pretend like the left-hand side is the height. And of course, as you see me do that on this problem, it overestimates the area, right? My rectangle's bigger than the actual area I should have gotten. Option number 2 says, okay, well, maybe I don't want to use the left-hand endpoint, I want to use the right-hand endpoint. I'll use the right side. Well, as you can see on this particular rectangle, this rectangle is actually smaller than the region that I wanted, right? And a third way that we're going to do is we're going to use the midpoint. We're going to say, okay, well, how about I use the halfway point? And I use the rectangle here. And on this particular piece, it's not true for every piece I draw this for, it looks like it balances it pretty nicely, right? I have a little bit that's overestimated and a little bit that's underestimated, so maybe it's a better estimate overall. And on this particular shape, right, that I've drawn, it may be. On other shapes, it may not. So we have 3 ways of approaching this. Left endpoints, right endpoints, and midpoints. Okay, so I'm going to draw them in really quickly, but it's going to be the images that I was sketching before. On this shape, yes.
Do we have to use a trapezoid in this?
We don't in this book. Yeah, it is another method. So you're exactly right. If I go over here, another way of doing this is you could create trapezoids. So if you take the the endpoints right here and you connect them with a line segment, it looks like this, and you can create as much trapezoids. And they often are a very good estimate. It's called the trapezoid rule. It doesn't lend itself well to continuing down the line of what we're going to do beyond that, which is why it's not that big of a topic right now. But yeah, there are other shapes we could use for sure, and a trapezoid would be a very nice one, in particular for this curve it would. So yeah, you're right. All right, so, and there's nothing special about the fact that I'm drawing 4 rectangles. I'm doing it because it's easy to draw, okay? We could draw 3 rectangles, you could draw 15 rectangles. It doesn't matter what the rectangle number is. Eventually, we're going to have lots and lots of rectangles, and I'll show you how we do that. But for the sake of drawing the pictures, 4 rectangles is sufficient. So in your shapes, I want you to draw essentially the same shape 4 times, right? Split the diagram up into 4 areas, approximately equal in width. And imagine that you're trying to, don't shade them in like I did a minute ago. I'm going to actually shade in the approximations I'm going to get. So if I'm using the left-hand points, it means when I take a look at this region right here, right, this width, I use the left side. So the left side of this would be this point. And I take that to be my height and I draw it over. And when I find my area, it's going to be the area of this red rectangle. It is an overestimate for sure on this particular region, right? It's more than the area underneath the curve. The next one piece, this next piece right here, I'll do that in blue. Again, it needs to be the left-hand side for this particular method. That's the blue dot, and I draw it straight over and down. Again, that blue rectangle overestimates my area. Okay, I'm going to try another one. We'll go with green. This left-hand endpoint actually does what? It underestimates the area. Okay, so it's not always an overestimate from one direction. It depends on the shape of the curve. And then my last one, I'll do in orange. What does it do? It underestimates again. So these 4 rectangles, if I add them together, I've got 2 of them that are overestimating, 2 of them that are underestimating. I might be pretty close to the actual area, actually, right? Because they kind of balance each other out, at least visually they seem to, in terms of the amount of area that I'm calculating. Let me see if there's anything else I want to say on this one before I go on. Yeah, oh yeah, there I am. Okay, so when you're calculating these pieces, you know how to find the area of a rectangle. Somebody tell me, how do you find the area of a rectangle? Height times width, or base times height, whatever language it is you want to do, right? Now, if I've done this, I don't want to say correctly because it's not necessarily that it's correct, it's just easy. If I've done this in the easiest way, then each one of my rectangles has the same width, right? So each of these pieces is the same. So this is like, we call it delta x, it's the change in x. All of these have the same width. Does that make sense? Obviously, it's much easier to calculate if they're all equal. Okay? They don't have to be equal for this process to work, by the way. It's just easier. So if I'm calculating each of these, and I want to calculate their area, I'm going to call this L of x because it's the left-hand endpoints, okay? I have 4 areas of rectangles, and they're supposed to be length times width. So I need to label these just so that I can have a reference point here. So I'm going to call this first point right here x0. The second sort of the points that I've made, x1. This piece is going to be called x2. This length is x3, and I'm going to end at x4. Okay, so are we good so far for everybody? Now, because this is an xy ordered pair, right, like y equals x, I'm sorry, I don't want to say it that way. F of x equals y, or something like that, like this curve. This particular point right here, it has to do with the function value, right? So if the red dot is the x0 location, then the y value here is f of x 0. That's the height. Whatever happens when I plug in x 0 in the equation, that's going to be the height that I get. So the thing is that the height here is whatever the y value is. Does that make sense? So this distance down here at the bottom, delta x, is being multiplied by whatever of the red, blue, green, or orange dots y value that I have, because that's the height. Height is the y value in this picture. So down here, if you're thinking about this, it's the first one, the red one, is delta x. In fact, let me use red. It's delta x times f of x 0. That's the first height. On my second rectangle, the blue one, it's delta x times f of x 1, because that's the height for my blue rectangle. And then I have another delta x times f of x 2 for the green rectangle. And then the orange rectangle, again, at the end, is delta x times f of x 3. I don't have a height at f of x 4 on this one, right? Because f of x 4, where it would be, I'll do it in purple, it'd be here. I don't have any rectangles at that height, do I? So I don't need the x4 for the purposes of this particular, equation, if you will, that I just created, okay, or expression that I just created. So taking a look at this, do you notice that every single piece that I've written here has delta x in it? Do you see that? So, yes, can you calculate this independently for separate areas? Absolutely, you can. But what you could do to make your process quicker, easier, is you could factor that delta x out, and then you just have the y values added together. F of x 0, f of x 1, f of x 2, and f of x 3. It's fewer steps. I add 4 pieces and I multiply once instead of multiplying 4 times and adding 4 times. Okay, does that make sense? I'd like to show you how this connects back to the summations that you just did. Okay, not because you have to connect them back every time you do them, but there is a connection, which is why we did the previous steps. If you take a look here, what this is actually saying is that this delta x is being multiplied by the summation of f of x sub I. In this case, it's going from I equals 0 to 3. That's actually what's happening here, right? This is saying add up all the f sub x sub i's from 0 to 3 and then multiply them by delta x. So there is a summation hidden inside of that. Okay, so we've taken a lot of time to go through the left-hand ones, which means that the right-hand ones are almost identical. We can go through them very quickly. So if you take a look at the right-hand image, okay, you're going to draw the same rectangles that you had before, or at least approximately so, the same widths. The difference is that instead of having the left-hand endpoints of each rectangle, you're going to have the right-hand endpoints. So on this first rectangle that I did in red before, the right-hand endpoint would be this point. And on the second one, the right endpoint would be this point. On the third one, the right-hand endpoint is this one. So the third one actually overestimates this time, right? Whereas the first two have underestimated. And then the last one would actually have this as my height. Okay? So whether they were overestimated or underestimated before, it's kind of they switched on this particular graph. And as you're taking a look at how we labeled them before, this is still x0, x1, x2, x3, and x4. And I still have my, and I'll call it R of x for right, for right endpoints, right, since I did L of x in the last one. I still have the delta x's times each one of them. The difference is now that my first height is not at f of x 0. What's my first height? It's at x1. right? That's where that red dot is showing up. So it's actually f of x1 plus f of x2 plus f of x3, and I include this time f of x4 because it is being used. And again, if you wanted to see that in that summation notation, because it's there, the only thing that actually changes at this time I equals 1 to 4 of f of xi. That's what's going on. Now midpoints are a little different. So let's take a look at the midpoint one here. Your image will start out the same, as in you draw the four, partitions is what it's called. It's called a partition of the interval. And what we'll do differently is how we will label and mark our rectangle's heights. So roughly, okay, it isn't perfect, but you get the right idea. So when I do the heights on these, it's a little bit different because I'm using a midpoint value. So on the first rectangle, the halfway point, which doesn't mean it's the halfway point in height, right? It just happens to look kind of like that on this. Looks something like this. And on the second one, it would be about right here. You have this piece. On the third one, about right here. So the height has to go to both edges, okay, like that. And on the third one, about right here. So we have this piece. Notice the widths of the rectangles are still the same. And notice there are still 4 rectangles. Yes, I subdivided my intervals to get the heights, but that doesn't actually mean that it changes the fact that I still have 4 rectangles with the same width as I had before. So I still have the same delta x being multiplied. I'm just doing it for different heights. And it's not got near as clear-cut a clean way of writing it like I did here for the r of x and the l of x, right? So when we do this calculation, I don't have that nice, neat form in which to write it down at the beginning, but the process when we actually do one works exactly the same. So let me show you how this works with an example. Okay, so this is the example we're going to do. You will want your calculator, so definitely grab your calculator out so that you can calculate these, because they can get, this is not a terribly messy equation, but they can get very messy depending on the equations that you're working with. This actually asks us for 3 things. So I mentioned before the last test, and actually Rod Anthony came up to me afterwards and said, man, that really helped. That when they're asking multiple things but they don't list it as A, B, C, sometimes it's really helpful to highlight or circle or underline to make sure you answer all the questions being asked. And this is a really good place where it says multiple things to do. It says use left endpoints, right endpoints, and midpoints to find 3 approximations. There are 3 calculations you're going to do with these directions, even though they aren't listed A, B, C. Are you with me? So we're going to calculate 3 times. The cool thing is that if you're using your calculator to calculate these in a concise way, you can manipulate your calculator to do it quicker, and I'm going to show you how to do that. Okay, so there's some cool features. So take a look here first. If you want to draw a picture to give yourself a reference point, that's helpful. At the very least, it's worth drawing a number line. So if you don't want to draw the whole picture, that's fine. I'm going to give a sketch of the picture, but a number line at the very least would be a helpful way to do this, to divvy up to partition up your interval. So this actually says that I'm going to go from 0 to 2. So I'm at 0 over here at the y-axis, and my interval is supposed to go out to 2. Okay? And it says I'm going to use how many rectangles? 4. Okay? Your problems are not always going to have 4 rectangles. Sometimes they could have 8, right? Or they could have 6. So you would subdivide accordingly. On this one, since it has 4 rectangles, I'm going to subdivide it into 4 regions. So these are going to be 1/2, and this would be like 1 1/2. So I'm going to write it as 3/2. If you want to use decimals and do 1.5, fabulous, good with that. So I've got 1/2, 1, 3/2, and 2. So whether you draw the picture or not, that lends itself very well to calculating and to writing out the calculation that you need. So without even drawing the picture, let me show you what I mean by that, and then I'll sketch the picture so that we can see what it's looking like maybe a little bit more clearly. So I tend to start with the left hand, but you don't have to. The first thing to recognize is the width. What is the width of each region that I've marked? It's 1/2, right? I can see that from the number line. I don't need a whole picture. The width is 1/2. And then I've got 4 rectangles, so I need 4 heights. And L of x means the left-hand endpoint. So I need to start at the far left-hand endpoint, which means I'm starting at 0. You with me? So I need f, is it called f, this one? Yeah. I need f of 0. And then I'm going to mark out, all 4 of them until I get to the 4th rectangle. So it's f of 0 on this number line, f of 1/2, f of 1, and f of 3/2. Those are the 4 left-hand endpoints, right? The first rectangle here, it'd be 0. The second rectangle would be 1/2. The third rectangle would be 1. And the fourth rectangle would be 3/2. Okay, is everybody good? Grab your calculator. Here's a cool calculator trick moment, okay? I wish I had a way to display my calculator in this room. I just don't. So I would like for you to put the equation in your calculator, 2x squared plus 5. What's that? I want to show you how to do the calculation without finding individual calculations. Let me just bear with me for a second. It may be something that you've seen before. Okay, so everybody in your regular plain screen after you put it in y1. So in y1 you're doing 2x squared plus 5, and in the regular screen it should just have a blank screen. Okay, everybody good? All right, I want you to hit vars. We've used vars before. Vars, go over to y-vars, choose function and y1, and then in parentheses put 0, but don't press enter. So right now your screen should look like this. It should say y1 of 0. Does your screen say that? Fabulous. Then put a plus sign. And do vars, y-vars, function y1, and do y1 of 1/2. And then do the same thing for y1 of 1 and y1 of 3/2. So if you go through and put all of those in, if you want to put in decimal form, of course, you can do that too. What did your calculator give you for a summation after you've plugged all that in? What did it do? 27. You're right. And I didn't do the 1/2 at the beginning, so this is really 1/2 of 27, right? So what's 1/2 of 27? What is it? 13.5, you bet. In decimal form or in fractional form if you wish, but 13.5 will work for me. Okay, but here's where it becomes super helpful. Are you ready for this? Let's write down r of x real quick. And then I'm going to show you what the cool thing is you can do in your calculator to save yourself time. So for r of x, it's still 1/2. What are the y1, or what are the y heights that I need for my heights of my 4 rectangles this time? It starts at where? At 1/2. So you're going to write that down for me, that you're starting at 1/2, that you have the number 1, that you have 3/2 or 1.5, and you'll end at 2 this time. Agreed?
What?
We're doing the 4 heights that correspond to the right-hand endpoints. So on this interval right here from 0 to 1/2, the right-hand endpoint's 1/2.
Just start at the right-hand side and work.
You can, but it's going to be easier for your calculator to do it the other way. But if you write it backwards, that's fine.
Oh, I swear you said my name. That's why I was like.
Oh, no, I didn't say your name, Reed.
No. I get it. I was
No.
just
Oh,
like,
okay.
stop it.
Sorry. No, I didn't say your name.
Just to read it. See, that's probably, I heard something like that. It happens all
Sorry.
the time.
That's what happens when your name's Reed, right?
My
Yeah.
mom's an English teacher too, so it doesn't really.
Nice. So nice. Okay, so here's what the cool thing is I want you to show you in your calculator. If you still have 27 as the last entry in your calculator, maybe you do, maybe you don't. If you do, I would like for you to hit second, enter. If you had division by 2 as your last step, do second, enter, do it twice. Second, enter, second, enter. What should happen in your calculator is it should pull up that exact text that you just wrote. it should still say now on my screen says y1 of 0 plus y1 of 0.5 plus y1 of 1 plus y1 of 1.5. Does everybody have that showing up where it's like it's the thing you're working on right now? Almost all of those are in the new calculation I want to do. What's different? The number 2, and I don't have
Zero.
the number 0. So if you will arrow back and change the 0 to a 2 and press enter, it did it all for you, and you did not have to go through y1 bars, all that stuff over again. It's a repeat feature, which is really pretty cool. Saves a lot of time. And if you've hit enter at this point now, what did you get for your heights, or for your summation before the 1/2? What was it? 35 is, yes, that is correct. Yes. And then what is 1/2 of 35? 17.5. Okay, is everybody good? All right, doing the midpoints is not quite as useful for that feature on your calculator. Whoops, didn't mean to do that. Let's try it again. But we can still use it a little bit. So for my midpoints, this is the one that I was like, we don't really have a very nice closed out form to rewrite this in. Remember, we did talk about the fact that there's still 4 rectangles and it still has a width of 1/2. But we do have to work a little bit more for the heights that we need. So take a look at this point. I'm supposed to be doing the midpoint of this interval. So what's the midpoint? What's halfway between 0 and 1/2? It's 1/4. What's halfway between 1/2 and 1? 3/4. Hopefully you're thinking in terms of money. That's how I think about quarters. How about between 1 and 1.5? 1 1/4. And if you want to change that, you can, or you can write it as 5/4, either way. And then halfway between 3/2 and 2. Yeah, it's 7/4, or you can do 1.75. So decimals work just fine. I don't have a problem with them. I'm just apparently in fraction mode right now. So, okay. I think decimals are what's on my notes, actually, but, you know. So my 4 heights are actually the red values that I've written in. So I'll write it with decimals just for fun now. So I have f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. Unfortunately, you can do the second enter in your calculator, that's fine, but then all of your numbers are probably not quite big enough or wide enough, perhaps depending on how you've written them in to make that work. Maybe they are, maybe they're not. So it might actually be just as quick to go through all the original steps as you do that. So you would calculate each of these values by plugging those values in and manipulating whatever you need to manipulate. There are insert buttons into your calculator if that's useful to you, or you can enter them from scratch. Okay, I have 30.5. Is that what yours worked out to be? Should check my notes. Okay. And then multiplied by the 1/2 in front. And if I have this right, it would be 15.25. And if you have it in fraction form, of course, you can leave your answer. All right, any questions on that? It's cool. It's good stuff. Yeah, there's a lot of calculation. It's one of those things where I don't know if there's other areas of your life where it's like tedious things and they don't require quite as much like hard thinking skills. It's just more routine. And some of us like those routine things, and some of us just find that super boring. So some people really like this stuff and some people don't. But that is section 4.2. So quiz from 4.1 and 4.2 will be happening on Friday.